What is the PMSM? How it is differ from previous motors, and what are the speed control mechanisms are available, how we can control the speed, and finally where it can be used in the real-time applications. So these topics we will discuss in detail. Please engage with the entire session. Definitely it will help you to know about know about more in PMSM. And so if you take a induction motor and synchronous motor, and then BLDC motor, PMSM motor. So PMSM motor has some unique features. So let us see how it is entirely different from the induction motor or synchronous motor or BLDC motor. Right. So this is a PMSM motor which is available in the market, and so generally this motor has a motor terminal. In addition to that, see here, this is the motor terminal. So this is the motor terminal, and then shaft. So it's it's industrial standards shaft, and then molded in the complete cylinder, in the complete box. See here, in this like this PMSM motor, you can get it in the market. Inside the motor, so there is a two major component. One is called stator and another one is called rotor. So in this motor, that is the static part, or stator has a magnet. Has a coil, right? So if you apply supply to this coil, then the resultant due to the resultant flux, that magnetic pole will get generated. Right. So inside the rotor, so it's a permanent magnet. So whenever the magnetic pole or magnetic pole generated in the stator, this rotor magnet will try to catch or try to align with the stator. So if you run the supply, entire supply, then the stator magnetic pole will try to revolve inside. Inside the stator. So finally that rotor will try to catch it, then it will follows, and then it will try to keep on continuous as per the stator magnetic pole. So this is the basic working principle, and again in detail we will discuss how it is working in the next slides. See here, if you want to understand more about synchronous PMSM, then we should know about what is induction motor and then what is synchronous motor. Similarly, what is the BLDC motor, or what is the synchronous motor, and then how that in the PMSM is differ from the synchronous motor. That thing we should know about it. So first let us take induction motor. So induction motor has a stator and then rotor, right? In the stator it has a coil. Similarly, rotor also has a coil. So sometime it will be terminated with the end ring. Otherwise it will be terminated with the external rheostat. So based on your application, you can choose the type. Similarly, so this for starting this motor, you should apply a supply to this stator, right? And once if you apply, then due to the magnetic flux linkage, then the rotor receives some forces. So that force will try to catch the stator synchronous speed. So but it will not be exact synchronous speed, so it will be some slip, so that there will be some lag. So that's why we are calling this as a asynchronous motor or induction motor. So due to this single excitation, we are calling this is a single excitation motor due to the apply of supply. That is only one supply we are going to apply into this motor, right? But in the case of synchronous motor, so it has a two coil similarly, but as per the induction motor, this motor also has a two coil. One is a stator coil and another is a rotor coil. But here the stator coil, if you want to start the machine, then we have to apply voltage to the rotor. Then only that whatever we apply the stator, but it won't start. When you start to apply a field winding, then only it will try to rotate. So that's why we are calling this is a double excitation, right? Similarly, that rotor speed will be equal to the stator synchronous speed, because we are applying voltage to the rotor, so that is a magnet. Again, it will electromagnet that will aligned with the stator synchronous frequency. So the rotor speed always equal to the stator synchronous frequency. So the stator synchronous frequency always it will be, that is 120 f by p, right? So from the basic formula we can understand how it is, what is a synchronous speed and all. And here we have to apply the three-phase input to the stator as well as the rotor supply, that is the rotor excitation. So like this we can understand what is a single excitation, then what is a double excitation, right? So now we know the synchronous motor. From this synchronous motor, how the PMSM has been deviated. See, let us take a synchronous motor as a stator and then rotor. Similarly, PMSM also has a stator and then rotor. But in the synchronous motor, rotor has a coil, right? Instead of rotor coil, it has a rotor magnet. So it's a permanent magnet. But in the case of synchronous motor, whenever you started to apply voltage to the rotor, then only the magnetic field will create. Right, so that is called electromagnet. But in the case of PMSM, so already the default magnets are there. So whenever you start apply voltage to the stator, then the rotor will try to catch the stator, right? So stator magnetic field, because already it's inside the rotor the magnet is there. So by this principle, the rotor will try to it will catch the magnetic stator magnetic pole. Then it will keep on continuous as per the magnetic stator magnetic pole. So whenever you change the commutation the stator supply, then it will automatically change the directions. So from this point we can understand how this synchronous motor is deviated from the PMSM. What is the PMSM actual working principle? So let us go for the we can discuss about what is a BLDC and then what is PMSM. Both machines are the synchronous machines, because both machines rotor speed will be equal to the stator supply frequency. For both motors, the rotor will try to, whenever you start applying to the voltage to the stator, then in the stator the rotating magnetic pole will get generated. So the rotor will try to catch the magnetic pole. Once if it is aligned, then so it will keep on follows its a magnetic pole path. So for the entire the 360 degree, it will try to rotate it. And by this method, the motor receiver force from the stator supply, then it will gives you the rotation, right? And similarly, BLDC motor, we know already, we have discussed in the previous sessions. BLDC motor is a DC machine, because the BLDC machine and the DC machine except the commutation, nothing other change. So in the BLDC, that's why we are calling it, this is a DC power supplied machine. And due to this behavior, the trapezoidal back EMF or flux density will be in the trapezoidal shape. So due to the trapezoidal shape, the current and back EMF, everything will be the trapezoidal. So if there is an absence of sinusoidal function, definitely the harmonics will be there inside the machine. So due to that, the torque fluctuations will be there comparatively, not exactly. I mean, the BLDC motor has an entire difficulties and all. I'm not telling like that. See here, if you compare with the BLDC and then PMSM, comparatively PMSM has a lower frequency harmonics, but BLDC has a higher harmonics. But if you compare with the DC motor, BLDC will be the best one. But if you compare with the PMSM will be the best one. And similarly, again, it depends your applications where you are going to use this motor. So it depends that target applications, then machines can be categorized by the optimal solutions. And similarly, that the BLDC and the PMSM will produce a constant torque at the entire power range. Similarly, whenever you change your torque value, that is input to torque value, then the speed will not get disturbed. So during the entire power range. Similarly, for the PMSM, again we are going to apply the AC supply to this motor, and due to this AC supply, the flux density will be the sinusoidal function. So due to that one, the back EMF of the motor will be the sinusoidal function. So due to that back EMF, it is a sinusoidal function. Then the stator current always it will be a sinusoidal function. So due to the stator current sinusoidal function, the harmonics will be almost maximum. It will be negligible amount only, but still it will be there. So due to our external power converter issues, then the harmonics also will be there. But because of the load issue, the harmonics almost negligible amount. And this motor will generate an entire power range. It's a constant speed as well as the constant torque. So if there is any changes under, then the torque will not be get affected. Similarly, it will produce you higher efficiency. And so the PMSM motor, again, we can understand in detail. So this motor has a stator as well as rotor, right? See here. So this is the stator winding, then rotor winding. The rotor has a permanent magnet. See again, this stator fixed with one reference frame. Right. Similarly, we can duplicate this motor rotor as rotor fixed part will be the inside one, and then outer part will be the rotor. So if you change this dimensions or constructions, then we can use wherever it is required. See, for example, for electric vehicles applications, then we can use this kind of constructions. That is the second method. So here again you have one more advantage. So these kind of motors will give you the perfect power, will give you at a higher maximum efficiency if you increase the diameter of the machine. So likely you can reduce the length of the machines. If you do that exercise, then we can match this as a exact wheel for any electric vehicles, any electric vehicle applications. So due to that behavior only, the EV vehicle in the future transportation will be entirely EV vehicle. So everybody try to replace with the induction machine. Earlier that EV vehicle all the EV vehicles, the induction machine only has been placed. But nowadays that BLDC and then PMSM, in sometimes some manufacturers are trying to using that SRM also, switch reluctance motor, and then synchronous reluctance motor also people are trying to use it. So there we can get a higher torque to handle the entire load without any disturbances. So due to this kind of behaviors, people are trying to use it. And again, if you take about the classifications, and before that we will check what is inside the machines. See, if you take about the entire motor, this is the stator core. Inside the stator core, the stator coil has spread the entire region. So again, here we can classify into two types. One is called distributed winding, another one is concentrated winding. So both, if the higher range of current, for example, if stator current itself about 100 ampere, then we can keep it as a concentrated winding. If it is a lower current rated winding, then we can keep it as a distributed winding. So similar like that, we can choose whatever we want. And after that, the rotor stator assembly will be there. And inside the rotor hub, see here magnets. These are all the magnets, and these are all the magnetic houses. So again, it is a steel plate. This is the steel plate. Inside the steel plate, this magnets is going to place it. See here, it's a small dimensions magnets. These are some piece of magnets. So based on our target applications, again we can classify it into variety of types. This PMSM. So based on the rotor position, rotor constructions, let us see one by one. See here the classifications, surface mount classification. So that is a one type, and another one is that interior mount PMSM. See, for example, in the rotor area, the magnets has placed over the surface of the outer area of the rotor. So this is called the surface mount PMSM. Similarly, the interior mount magnet rotor type PMSM. So here the magnets is placed inside the machine. See, actually this behavior will give you strong magnetic field, and again we can increase some by adding additional magnets, so that we can increase the magnetic field as a very strong thing. So in that case, the pulsating torque will not be there, and the torque density definitely it will be high. So if there is any fluctuations in the speed, or if there is a fluctuations in the load, then the motor will keep its original constant torque, so that it can give you the smooth operations. And again, we can classify into variety of rotor types. So here you can get a lot of chance to work in the research area. You can modify the rotor dimensions. You can keep variety of you can change your magnetic types, and you can change the magnets placement area of the rotor. So by changing these methods, we can increase or we can vary the motor performances. So by this method, we can do a lot in this research. This all comes under the machine design part. And so PMSM characteristics about it. So these are some theoretical part. So just to check it. And by default, here I should mention one thing. So it has a very smooth, due to the very smooth operations, then the noise of the machine is absolutely it's zero comparatively for the previous machines. And then heights, we can extend the speed at any range based on that motor dimensions. We can get that speed. Similarly, comparative, see for example, if you take a 1 HP machine of PMSM, similarly take 1 HP induction motor. So if you compare the both motor size, comparatively PMSM will have a lesser size than the induction machine. And similarly that the synchronous machine, but both the BLDC and then PMSM has a lesser size. So for due to that lesser size, we can use, or we can easily replace the previous methods. And if you take about speed control topic to the motor, see in existing method, if you take a 3-phase induction motor, you can directly connect to the RYB system, then the motor will try to give you. So by keeping any rheostats, then the motor will try to give you the proper solutions. But if you take about a synchronous motor, so if you connect directly to the three-phase RYB system, then it will gives you the speed, but it will not be exact speed, exact performance. So this is not a right way to operate the machine. That is a PMSM machine. So in that case, we have to keep at any point of time, we have to keep position sensor and then inverter. Then only we can get a maximum output from this machine. Otherwise, it will be like a induction machine. And in the case of speed control, see, this is again a basic speed control mechanism of the induction PMSM motor. Still, options again, we can start the motor without Hall sensors data also, but I will show you that one demonstration how it is operating. That will give you improper results. Still, the motor will try to run. Still, the motor will run the entire period, and then it will give you some. It will generate some amount of torque. But if you cannot load the motor to anywhere, right? So due to that principle, so we have to imply the Hall sensors data, and speed regulations. Then only we can control the machine perfect. Otherwise, it will not exactly. So let us check the demonstrations. See here, I already developed this thing, this model. So I will explain you each and every model. So this is the DC voltage source, and this is a universal bridge. So here I used MOSFET, and again the 3 legs are there. No need to change anything. And this is a permanent magnet synchronous machine, and options is So this is, here we have to choose the sinusoidal function, not a trapezoidal. If you choose a trapezoidal, then it will act as a BLDC. If you choose a sinusoidal, then it will act as a PMSM. Right? And again we have to add the bus selector to get the motor parameters. Right? And this is the three-phase voltage and current measurement block. I will use this motor in the for further things also. We'll try to use this one. So this is a three-phase voltage measurement. Like this is a voltage measurement and this is a three-phase AC voltage measurement. Here you can get you can measure voltage as well as the current. And so this is a PWM generator, just a three-phase PWM generator. Use this functions. So it's an unsynchronized carrier frequency is the 27 into 50 hertz. Here you can use whatever you want actually. So based on the thing it will gives you. So here you can change the frequency. So by changing the frequency also, we cannot get the exact speed control. So for that speed control, it's again we have another demo. So let us check how we can control the speed. So then you can connect the thing, then the voltage you just apply 400 voltage, whatever you want. And the motor speed actually here, here we can mention we can check those details, whatever the things are available. See here the poles, number of poles, and then torque, everything will be there. So we can check it. And if you run the simulation, so you will get a speed running at 100 radian per second. So this is not a RPM, it's a radian per second. See here, so it's the motor is be a constant torque machine. So whenever the torque changes, see here at the point of, see initially initial value it will be 10. And then at step time 3, then it is a minus 10. So during that period, see here there is a speed oscillations. So huge oscillations is there. So by implementing proper control algorithm, we can regulate this speed also. We can minimize the speed oscillations. So again see here, so again this is the speed graph and then electromagnetic this is the electromagnetic graph and the stator current graph. So actually due to the sinusoidal function, so here the current shape will be sine functions. So this is sine functions. So due to this behavior, harmonics are comparatively less than the BLDC motor. Right? Similarly, let us take a PMSM motor with one more closed loop control mechanism. This is the second simulation. So both the simulations will be available in the LMS portal. Both LMS portal, you can check it and you can download the simulation and try to use this one. And similarly, this particular simulation is available in the MATLAB also. So by using that simulation, we can understand how the speed control mechanism is clearly used. So for this one, we will let us discuss one by one how this how this simulation has all its parts. So this is a PMSM motor, sinusoidal function motor, and all the parameters has been mentioned here. Again, in this motor, by changing this number of phases, so instead of 3, you can use 5 phases also, so that you can, for higher power range, we can use higher number of phases to handle those powers. Okay, so to handle that maximum amount of power, then we can use this facility. And similarly, this is the PWM inverter. Again, it's another method of PWM inverter. I will tell you finally. And these are the bus selectors. So once if you connect to the motor, then the bus selector will sense the entire machine parameter to the measurable value. Similarly, here we are measuring the motor currents because it is a mandatory to sense the motor current. Similarly, here we are measuring the motor speed and then angular theta and electromagnetic torque. So this electromagnetic torque is for our visible purpose we chosen. But we need to measure, or we need to identify the motor speed as well as the theta value. So from this two data only we are going to get a PWM signal. First we have to regulate the speed, right? So it's being a 4-pole synchronous motor, so we have multiplied with 4 data and this is compared with reference speed. So this is into not RPM, it's a radian per second, and I again compared with the reference speed by using that some block. So this block again given to the PI block. So from this PI block will give you the rated current, reference current. So this current is maximum value is 30 ampere, then lower limit will be the minus 30 ampere. Okay, so once if you got the IQ reference, this is called IQ reference, and then ID and I naught let us take as it is 0. So because in the real time for the simulation purpose we can take it this as a 0, but in real time applications this the theta value and this reference we have to get it from the resolver component which is available in the motor. Along with the motor will be there. The manufacturer will give you the those details. And similarly, see here, so these 4 signals has been taken, and this is the ABC converter. So DQ to ABC converter. So these are all the MATLAB functions. See what it is. See if you take this is called U1, and then this is a U1 and U2 and U3. U4, right? So this each and every function it gives you some value. I mentioned appropriate signal name. So U1 of into cos pi. So generally we did DQ to ABC conversion. So for ABC how we can get a ABC value? Suppose if you take a VA, then VA equal to VD into cos theta minus VQ into sin theta. So like that it will be there for VA function. Similarly VB, same formula, VQ minus VQ sin theta of minus 2 pi. That is at 2 pi by 3. That is 120 degree phase displacement for V phase. Similarly C phase again 240 degree phase displacement from the A phase. So for each 3 phases will be apart 120 electrical degree. So this is the reference voltage for the reference current for the current generator. Right. So here again this is the reference current, and actual current we are measuring from the motor. So for the in real time applications we have to use current sensors, so that we can sense this value. Otherwise in the simulation by default this PMSM block will give you the data. So we are using that the same data, right? So once if you got this value, so here this is just like a comparator value. Again this is current, you know that a function of hysteresis. So whenever the input signal reaches my higher value or lower value, then it will generate a ceiling limit. So let us explain. Let us take this is IABC and then this is IABC reference. See here we are comparing this reference from actual to reference value. Then that error is limited with the maximum value. So whenever it reaches the 0.05, then it will emit 155. That is a maximum value. So here only we are equating the actual voltage. See now we need a 440 voltage maximum at a motor terminal. So here for A phase maximum voltage is the 155, similarly minus negative 155. And for B phase, again same criteria. See here the same criteria, 155 minus 155. Whenever it crosses that this value, the error value reaches the minus 0.5 and minus plus 0.5, then it will emit that value. And again for the C phase, same procedure for the C phase, right? So once if it is created, then this is the voltage controlled graph. Okay, so this is voltage controlled block. So this block is will generate these are all the signal, and then this is the power ground. So with respect to ground, we can check it as it gives you the 440 voltage maximum. So by this method, we are generating the voltage to the inverter, right? So voltage to the motor. So by applying this voltage, then we are we are trying to run the machine. See here, now we have to understand how this motor will give you the constant speed at any torque fluctuations. See here, to this simulation, 700 is the reference speed, right? If you run the simulation, see 0 to 700 it has reached. So during that, see this here we are the torque has changed. See, initially the 0.04, that is the step time. 0.04, the entire simulation time is 0.06. So at the time of 0.04, the torque is minimized. That is that we are reducing the load from the motor, right? So initially it is a 3 Newton meter. Then at the 0.04, it's a 1 Newton meter. So at that point, also, if you take a 0.03, if you enlarge the value, so the speed will be almost, completely it is an equal value. Okay, so due to this only we are calling it is a constant torque machine. So this behavior will give you the exact smooth operation to the load. So in that point of view, we can extend this application everywhere, wherever it is required, like AC motor, AC control, and then washing machine, wherever you need to operate higher operating called smooth operating functionality called robotic arm, and to handle that heavy load. So those things and all we can use this motor. And similarly voltage, these are all the voltage from graph, you can check it. So the simulation will be loaded in the LMS portal. You can just download that thing and then we will try to use it. So like this we can understand the PMSM motor principle. And again, this is a very basic speed control method, but still we can increase the motor performance by adding additional controlling method called vector control method we can implement, and then FOC method we can implement, and finally again we can add some intelligent controllers called fuzzy controller or neural network controller also we can add it. So that we can so we can get we can extract the entire performance from this motor. So that facility is available with this motor. And application point of view, in this application point of view, AC drives and automated guided vehicles called the electric vehicles, this motor will completely suitable, and heating applications, and then ventilating applications, air conditioning applications, for everything this motor is a perfect motor. What is actually that Blue Star and other manufacturers released AC with the PMSM machines. And robot, say again, if you take about robotic applications for to handle a huge amount of load, this robots has used wherever the robot used for huge load applications, the PMSM will gives the perfect solutions. And servo drives, for industrial applications called food processing industry or textile industry, wherever it is, that servo drive, wherever the DC servo you earlier used, then we can replace those servo drives with this PMSM machines. And again, home applications, AC, washing machine, and fridge, whatever it is, then we can replace smoothly with the PMSM.